A general Markov queue has constant service Si is lambda s regardless of what state it's in, but its arrivals decrease as the state goes up, kind of like people see a long line and they turn away. So its arrivals are ai is 1 over 1 plus I lambda a. This is good for I is equal to 0, 1, 2, 3, etc. And we're asked, well, what is the steady state queue length for this distribution? And then secondly, we're asked, what are the most likely states of the queue in steady state? For long lines, the AI will be very, very small, and the SI would just be constant. And so it makes sense that there would be a steady state. And so, as we know, we compute the sum 1 plus A0 over S1 plus A0 A1 over S1 S2 plus A0 A1 A2 over S1 S2 S3, etc. And then we just define R to be lambda A over lambda S, and so that would give us 1 plus R squared over 2 plus R cubed over 3 factorial plus R to the fourth over 4 factorial, plus. Then we recognize that this is just the series expansion of the exponential of R, meaning that the steady state exists because it's finite, and that pi 0 is 1 over this number, or in other words, the exponential of minus R. From the general steady state pi equations, we know that pi I is A0 times A1 times ... times AI minus 1 over S1, S2, ... up to SI times pi 0. So if we substitute those in again, we find that we get R to the I over I factorial times pi 0, which is the exponential of minus R. And this is good for I 0, 1, 2, 3, 4, etc. Well, we can recognize this as our beloved R Poisson probability mass function. And then we also notice that pi I over pi I minus 1 is equal to R over I, which is greater than 1 when R is greater than I, and it's less than 1 when R is less than I. This means that the most likely value of I, such that pi I is its maximum, is I is equal to the integer part of R when R is not an integer, and when R is an integer, there's two most equally likely values. I is equal to R minus 1 and R. Of course, this we already knew from the Poisson distribution.